The first session of Thursday, and Warrick is going to talk about modeling formal language in GF. Go ahead.
Okay, so yeah, this is kind of a prelude to my thesis, which is due next month, my master's thesis with Arne as my advisor. And yeah, so basically just one prior remark is I want and welcome feedback. So anything about the content, style, delivery, whatever, I welcome, either privately via correspondence or in the after chat of the whatever Q&A. So for the table of contents, yeah, so first we're gonna explore an abstract relationship between mathematics, computer science, with type theory kind of being the label we apply to computer science, linguistics and logic, which isn't listed here. And then we're gonna give hopefully a practical and brief intro to Martin Liv type theory and AGDA, which is pretty much impossible to do in such a short time period, but maybe from the perspective of this work, it can be a, yeah, kind of informal, but still relevant view of these topics. Then we'll go through some GF grammars, elaborating the abstractions we detail between CS, type theory, and linguistics and logic. And then, yeah, some afterthoughts, work to do, things of a kind of conclusive nature. So, yeah, here is a slide of just all the abbreviations used in this. I don't know if it's worth it to say them out loud, but I'm not a big fan of acronyms, and I think our language is so full of them, but I hope at least this is a manageable number of acronyms for most people, at least if you have familiarity with some of the things on here, you can kind of get the gist of what others may be. Oh yeah, and these slides, I haven't put a link up to the GitHub, but they're available there, so you can just go check them out. So the first slide of real content or substance is one comparing what we'll call a computer scientist analysis of language, like from the programming language implementation perspective, in opposition to the linguistic perspective on natural language. So we call those the abstraction ladders. And the left-hand side is what you would see in a typical compiler's course. So you take your strings, you lexically analyze them into lexemes, you parse them into trees, and that's what GF's doing for you, and it's also doing the reverse direction. Then if you have a decent programming language, the type checker will convert your abstract syntax trees into possibly, yeah, we'll check if they're well typed. And that could either be via checker or an inference algorithm. And then there's some downriver stuff happening with the code generation or interpretation evaluation into either some notion of value, either given by an operational semantics, or you could just do some kind of, yeah, code translation to whatever machine code, binary, etc. So then on the linguistic side, you're going to go from phonological phenomenon. So let's just say phonemes, and then you're going to have morphemes. Then there's some kind of syntactic representation. Let's just say that's due to Chomsky, and that kind of bled into the programming language community. And there's many different possible syntaxes for representing natural language. So that's why we have the set bracket notation. Then we have, a semantic side. So you could either go in the Montague tradition of higher order logic to some kind of simply typed lambda calculus, or you could take the dependently typed approach via Ranta and his 94 magnum opus type theoretical grammar. But then there's other abstractions which aren't so easy to encode in a diagram, and which I don't personally know very much about, but you could say what happens after a semantic understanding of a phrase or sentence, and then you could ask how is it encoded in the brain via like what Chomsky calls the I language, which may or may not be in dispute among linguists, but let's just include it for completeness. And then at some point the language gets generated again. It's kind of a circular process. So we complete the circle, whereas the target language doesn't generate strings it can. You could write a program to generate syntax for a programming language, but generally it's evaluating a function or doing some outside work. So I think these are just important to keep in mind for the scope of this talk. Okay, so this is what Robert Harper calls computational Trinitarianism. And it's basically a paradigm through which to view these subjects we call math, computer science, and logic. And it's somewhat of a joking phrase, but it's also very serious as well, in the sense that if you want to understand any of these disciplines, that it's kind of a degenerate understanding in some sense if you can't map them into the other disciplines. So I'll just kind of go around the circle. So from math to logic, math is kind of done in first order logic. So embedding math into logic, it's kind of already there. But then we can also go backwards from logic to mathematics. And that would be some kind of denotational semantics, where you take a syntactic phrase and give it a mathematical formula, maybe give it a truth value if it's propositional logic, or construct a model if it's first order logic. From math to computer science, we have interactive theorem provers from one side, so you can implement math in a programming language via, in our case, Agda, but others like Calc or Lean or Hull, or there's a bunch of theorem provers. And we'll see more of that later. Then from the CS to math side, we have the denotational semantics as well. So you can have a set theoretic semantics or categorical semantics. Buzzwords that might ring a bell in that direction would be like categories of families, de Beer, or there's lots of ways to model a programming language in mathematics. And then there's this top right direction between computer science and logic, which is the so-called Curry-Howard correspondence, propositions as types, and or Brouwer-Heiting-Kolmogorov interpretation of logic, where basically you include terms, proof terms, that encode some kind of justification of your proposition, that the computer can give you evidence that, justifies that you constructed something of that type. So you include the terms if you want to go from logic to computer science, where somehow the term encodes everything that needs to be known. And that's where type inference comes into play, so that you can reconstruct the type from a term. That's not always the case, especially with dependently typed languages, as we'll see. But you can also just remove terms and take a programming language internal logic turn it into logic. And in some ways, I guess this isn't an isomorphism as it's so often incorrectly called, because there's many ways of appending a term to a given logic. So let's now take a step back and ask a kind of, meta question is like, how does linguistics relate to this Trinitarian doctrine? So in this slide, we just show like linguistics in the center, and we're just talking about semantics in this case, but you could look at it through a syntactic paradigm, a pragmatic paradigm, etc. So if you take language and analyze it via logic, like higher order logic, that's Montague semantics, and in that tradition, if you interpret it in the semantics of a sentence in type theory, then that's Ronta's type theoretical semantics. Or maybe in math, maybe we just say like, this is vector spaces and you're asking for word embeddings of some sort, where they're just vectors in a high dimensional space, and then you can compare them for distance or other measures of similarity. But these aren't meant to be like canonical. This is just an example. And then if we go in the reverse direction, we could also say, how do we go from math to linguistics? We could say we have the language of mathematics by Gunnar Sellingham. We could embed logic into linguistics and just say logic is the set of phrases that in some sense have logical meaning, which is maybe a circular way of phrasing that, but you could just say it's a subset of natural language. And then you could also go from the type theoretical perspective, and this is what Martin Löf did in his 1979 paper on the meaning, now I'm forgetting the name off the top of my head, but constructive mathematics and computer programming. And he introduces the meaning explanations, where he kind of reduces type theory to a natural language justification. So the meaning explanations are called the natural semantics. So in some sense, he wants to evade formality by producing them, by taking type theoretical concepts and reducing them to some kind of natural language. So then we can also look at this perspective just from this subset of linguistics that we identify with GF, which is a very small subset, obviously. So we could say, how do we embed these three different Trinitarian doctrines into GF? And that would be via these three grammars that we present later in the thesis. So two of them are due to Arne, and one is from 2011, one is from 2014. And the other I developed, but it's based off a parser that was used in the cubicle TT programming language developed at Chalmers in Gothenburg. And then, from the other direction, we can say, how do we understand GF from these three perspectives? How do we construct a model of GF in these three perspectives in some sense? And there's this whole theory of operads, which is like categories with multiple in and out boxes. There's, the parser specification for GF is kind of given at a high level via inference rules. So in some sense, you could say that parser specification is a model of GF in some logic. And you could also say that, you can either see GF as a direct implementation of Martin Löf type theory, or you can embed it into Agda, which in some sense is a manifestation of Martin Löf type theory. So let's, quote Harper again, or quote him for the first time, but reference him again. So he says, concrete syntax is in some sense where programming meets psychology. And I think that's a good perspective to have when looking at GF and how to model a programming language. So we could say that the Trinitarian doctrine as proclaimed is purely formal. So you're just constructing models of one thing, of one space and another. But you could say that the linguistics is, yeah, partially informal, and it's also a lot less explored, I would kind of claim, partially because linguistics is so much less understood in some sense than these other fields. It's very empirically based. So this introduces many philosophical concerns. This Trinitarianism plus linguistics, or plus GF, the GF subset of linguistics that we present here. And I just kind of give this suggestion because Wittgenstein was all about language and meaning, and the philosophy of language was derived from him. So, and its relation in some sense to formal systems can be thought of as like directly emanating from his work, either, yeah, like explicitly or implicitly. So we suggest rereading Wittgenstein under this guise of Trinitarian doctrine plus linguistics. Let's just name the predecessors to remind ourselves that Frege was the first to invent what's called a formal proof, which we'll define more completely later, and predicate logic or first order logic, in which to do these formal proofs and formalizing what that means, what a proof is. Russell invented type theory to resolve his paradox, and yeah, kind of this notion of universes, because yeah, I guess most people are familiar with the Russell paradox. I don't want to butcher it by trying to say it off the top of my head. And then Brouwer, who was a mathematician in opposition to Hilbert in some sense, yeah, talked about constructivism, and constructive mathematics is the paradigm for doing mathematics. Mathematics is a social process. And yeah, that's kind of what led, these are all predecessors of Martin-Liff type theory. And then other names, Heiting, Kolmogorov, Church, Gödel, Kleene, Bishop, and many more I'm either unfamiliar with or forgetting. So let's just start with this famous Martin-Liff quote at the beginning of these lectures he gave in 1980, shortly after the publication of Constructive Mathematics and Computer Programming, where he renounced extensional type theory and went intentional. And so this kind of forms the lecture notes that were produced from this lecture kind of form the most canonical reference in all of type theory literature. So he begins with this statement: mathematical logic and the relation between logic and mathematics have been interpreted in at least 3 different ways. Mathematical logic as symbolic logic, or logic using mathematical symbolism, mathematical logic as foundations or philosophy of mathematics, and mathematical logic as logic studied by mathematical methods as a branch of mathematics. We shall here mainly be interested in mathematical logic in the second sense. What we shall do is also mathematical logic in the first sense, but certainly not in the third. So yeah, I think this is obviously an indication of the, I don't know, philosophical kind of momentum behind Martin-Liff. And we hope that this quote is elaborated a little bit and clarified a little bit in the writing of this thesis. I think it's a very deep way to start a presentation. So first, we'll just talk about this propositions as types comparison, and we'll just look at the names of the constructors, because like I said, this is an informal introduction to type theory from the perspective of translation. So yeah, so we have the for all and pi types, what's called pi types, which is the dependent product type. The sigma type is the exists notion in logic. We have the horseshoe, which is implication or function in type theory. And since GF is a functional programming, this is probably the most intimate of the types. Then we also have products and co-products. So products are given by the and in logic, co-products given by the or disjunction, and negation, top and bottom. I kind of use the same syntax to suggest that, yeah, there are some very deep relationships. And then there's this equality symbol versus the equivalence symbol. And that's because I guess we're saying this is definitional equality in the type theory sense. So type theory, dependent type theory, has two notions of equality, that which can be computed and that which is type. And we'll get into that more later, but I'm just showing this syntactic comparison for those unfamiliar. Then there's also sets and types. So when we do math in the classical sense, in the math department sense, we have logic, and then we talk about the propositions, and then there's the sets that are kind of just objects, which we talk about in our propositions. So in the type theory side, there's no distinction, or at least in classical Martin-Liff type theory or the type theory we talk about, there's only types. So the natural numbers are just given a type nat. The product of two sets, so the natural numbers is just seen as a set. The product is a set. If you've taken an intro to set theory course or seen any of the axioms of Zermenko, yeah. Now I'm forgetting how to pronounce this, but yeah. So we have the Cartesian product, or we have the product type. And if you notice on the previous slide, that's also the and proposition. So in classical mathematics, you distinguish between Cartesian products and conjunction of propositions, whereas in type theory, you have the same constructor for both. There's also functions, which are distinguished in set theory from implication. You have predicates, which are also sets, but those are just sigma types in type theory. Then we have some question marks. Well, we have the bottom type and the empty set, which in some sense are filling the same role, but then there's no notion of a biggest set. So there's a question mark for what is the top type to be interpreted as in set theory. And on the other hand, there's a union of two sets or an intersection, which is not listed. And we don't have that naturally in type theory. There are union types and intersection types, but that's not in traditional Martin-Liff type theory. And I guess, yeah, there's many type theories to try to capture many things about classical mathematics, and they haven't all been integrated into a single unified framework, which is in dispute if that would ever be possible or feasible or desirable. And then there's things like universes, which sets don't have. I mean, I guess there's classes and there's things like cardinality and, yeah, constructing numbers of higher cardinality or sets of higher cardinality. And in some sense, yeah, that can be modeled in type theory, but it's not analogous to universes. But in some ways, that's how I think about it, even if it's not mathematically correct. And then there's also sets in, yeah, just numbers. The natural numbers are defined as sets in classical set theory, whereas they're just programs in type theory. Now we have judgments. So this is one of Martin Löf's big contributions, is to put the notion of a judgment at the epicenter of doing mathematics. So there's 4 judgments: that of a type, that of 2 types being equal, the inhabitation of a type by a term, and the equality of 2 terms, definitional equality or judgmental equality. And in classical mathematics, there's only 2 propositions. It's that P is a proposition and that P is true. And so it's less, it's kind of been filtered in some sense of what makes type theory interesting, which is computing with types. So judgmental equality is uniquely type theoretic, because judgments in type theory are decidable and truth or inhabitation is not decidable. So P versus NP remains unsolved, and we don't know if it will ever be solved. So it's an undecided proposition. And there's many other propositions which are currently open problems in mathematics. So there's also more exotic judgments available in other type theories, like P is possible. So if you took a Curry-Howard perspective on modal logic, for instance, and you were trying to figure out a programming language for it, you could ask what judgments in this programming language capture this logical phenomenon, but we won't get into that here. So let's just compare type theory and classical first-order logic briefly. So the rules of types make explicit that they're not equivalent to those of classical first-order logic. So if you haven't seen these rules of type theory, that's like one of the kind of syntactic horrors that you have to go through as a student. But once you get used to it, it becomes very clear. But the elimination rules of like the exists or the sigma type are very different in some sense. And yeah, also part of that is because an existential assertion in type theory requires data. So to say there exists something such that blah, 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 you have to give a witness and an object that the witness, or a proof that the witness satisfies the predicate. The law of excluded middle and double negations are not admitted in Martin Löf type theory, which they're often used in mathematics, but the type theorists would say they should be used as reluctantly as possible. Then there's also the, this simple linguistic example of to be not unhappy is a clear differentiation from being happy, and you would say them to mean different things. So it's kind of natural language evidence that we should be dubious of excluded middle, or at least reluctant to use it when we don't have to. And this difference in the foundations makes our approach to general translation via GF of non-constructive mathematics most likely impossible, at least so that it type checks. But perhaps it is possible for other type theories, at least for certain subsets of mathematics. So like Hull or one of these other theorem provers, which I'm not familiar with, but don't use dependent type theory as their foundation or kernel. So other issues, one doesn't define logics and type systems in mathematics. Encoding concepts like rationals and reals in type theory are difficult. Sets are just one way of encoding mathematics, and yeah, types provide another perspective on what it means to construct something. So yeah, we can just say that there's already debates within the mathematics community, computer scientists aside, like category theorists and set theorists, about things like small and large categories, higher categories, all these things that come from the categorical perspective. they kind of make the category theorists think that, oh, this is better than set theory, but obviously there's a lot of reluctance from the set theorists. I just use these big words here without even knowing that much about what they mean, but I think they're relevant if anyone's interested. And intentional type theory, as we said, comes with two notions of equality. So judgmental, definitional, or computational, those are all interchangeable and propositional. So let's just give one example of what a type theoretic statement or type would look like. So there's this classic phrase from Montague, every man who owns a donkey beats it. And I guess the genesis of Martin-Liff type theory and the post-Montague tradition of linguistic semantics came from Martin-Liff and Göran Sundholm. I don't know how to, is it Göran or Göran? But they were talking over dinner and Martin-Liff like apparently wrote this on the back of a napkin, how to encode this where you interpret common nouns as types. So this just says for all Z in the type of, if there exists a man and there exists a donkey such that the man owns the donkey. So for all entities of donkey, man, and ownership triple, then we can produce something of the type that the first projection of that matched with the first projection of the second projection. So the man beats the donkey. So yeah, this is just an example. We don't have to understand it, but it's famous and it's relevant for this because it kind of led to GF being created. So homotopy type theory, even more degenerate introduction to a very beautiful and worthwhile subject that we won't have time for to at least discuss any of the, big details, but hopefully we can shed some light on why it's interesting. So it's, coming to terms with what equality means in type theory. And this is a very confusing detail for mathematicians trying to learn type theory because they see computation as something innate. But the whole idea of homotopy type theory is that by distinguishing those, you can see the propositional equality types as topological spaces. So you can iterate them. So you can say, given some type, we can form a path between 2 points in that space. So if X and Y are points, then this equality means there's a path between those two members of that space. And then you can say, okay, now that we have, now if we have two paths between X and Y, we can deform one path into another. And that's what the topologist calls a homotopy. But from type theory perspective, it's just a way of iterating that. And it's a little bit confusing at first because why would anything be equal to something other than itself? But there's this whole, exploration of this idea of uniqueness of identity proofs and other such matters that we won't discuss here, but just know that it's not an absurdity to write X equals Y until you know that X is equal to itself, because maybe the space has holes in it, or maybe the space is disjoint. And so different paths in the space may indicate structure about that space in terms of how they deform into each other. So the univalence axiom says that equivalence is equivalent to equality. So that means that if you have equality is kind of identification of two things, and equivalence is saying that you can transform two things. So if you have a transformation between two things, then you can transform that into an identification. in some sense, is what univalence tells us. And yeah, as I've said, it allows us to admit a topological interpretation and has led to higher inductive types where we can actually give explicit ways of constructing these topological spaces. So yeah, let's just show a slide with interpretations of the judgment T has type tau, because it's kind of the central judgment in some sense. So in set theory, you say n is an element of the natural numbers. In type theory, you say n is a term of type n, which is just a reiteration of this with n and n substituted for T and tau. In homotopy theory, you could say n is a point in the space of natural numbers. In category theory, n is an arrow between the object n and itself. And in logic, n is a proof of the proposition n, which is kind of broken, which is why the Curry-Howard isomorphism is so misnamed, because in some sense that's a broken interpretation. So what is AGDA? It's an implementation of Martin-Liff type theory, a logical framework, kind of like GF. So it just has a small kernel in some sense where pi and sigma give you an incredible amount of expressive power. You have an interactive proof development environment. You have inductive types, modules, pattern matching, and more. We'll see examples of this later. You have a large standard library and many other libraries adjacent to it, some deprecated. Forks of AGDA, like cubical AGDA or AGDA flat, etc. There's universes in AGDA, and there's tons of experimental stuff. I just gave a few examples: size types, conduction, tactic development, etc. So let's just compare the syntax from mathematics and AGDA. You have theorem, proof, lemma, axiom, definition, example, and I forgot corollary, but it's the same. So in AGDA, there's basically just these basic declarations. So postulate says there's no term associated with the type, but it's not recommended to use it in AGDA in some sense because it breaks the computational power of it. So definition is just when a mathematician says we define a homomorphism between two groups, those two groups would be included in this stuff here. And you just say, this is how you say predicate in type theory. You say it's a map from a type to a set, which is the universe, or it's just the type of types. And obviously that goes back to Russell's paradox. So there's a hierarchy of sets or types, but we won't get into that. Yeah, there's theorem statement and proof. So you just, say that a theorem has type T that's just how you make a theorem statement in AGDA. Same with lemma and examples. So there's a much more degenerate class of things, and that's kind of because, the difference between corollary, lemma, and theorem, according to a mathematician, is a semantic one. It's not of a formal difference. It's like they're just used in different ways. So corollary is kind of meant to validate a theorem, or it's validated by a theorem. And a lemma is a predecessor to a theorem. And a theorem is somehow this more important category of proposition. And so let's just look at, so this is the AGDA syntax on the right, but before going into that, let's just look at an example from mathematics, a famous example, and then the AGDA code. So I took this example from Martin Escardo's notes on homotopy type theory. So a twin prime is a prime number that is either less than 2, or either 2 less or 2 more than another prime number. So we could give another characterization of that, and then the theorem says there are infinitely many twin primes. So yeah, basically you can just keep finding twin primes bigger than the previous pair, and no matter, that's the idea. And so this is how you say it in AGDA. So you say to be prime in AGDA is a predicate over the natural numbers. So give a natural number and map it to a type. And you say that it's a number is prime if it's greater than 2, and if for all x and y in the natural numbers, if they multiply to that number, then x is either 1 or n itself. And that would carry the corollary that y is either 1 or n itself too. And the twin prime conjecture, this is kind of Agda's way of saying there's infinitely many things. So for every n, for every natural number, there's a number greater than it such that that number and its 2 plus that number are both prime. And that's what a twin prime is. So yeah, these details maybe we should just forgo here, but just know that there's kind of, if you want to compare the syntax to get an idea of one, because you know one better than the other, presumably you've seen some natural number or natural language proofs and you want to see what they look like in a theorem prover. That's, hopefully these slides will give you a good primer. So what is a proof? A proof is what makes a judgment evident. And that's going back to Martin Luss. Role in bringing out judgments is this kind of central thing in mathematics that was less acknowledged or unacknowledged prior. Gunnasalingham's quote, "There's a considerable gap between what mathematicians claim is true and what they believe, and this match causes a number of serious linguistics problems." And he does this very elaborate analysis of natural language mathematics from a linguistic perspective in his book called The Language of Mathematics. And yeah, it's an important reference for this work, but we won't go too much into the details. So let's talk about informal and formal proofs. We just kind of have this table where we have comparisons of the different categories or dimensions in which you can compare them. So a formal proof is done by both a programming language and a human, or a logic, maybe it's another, doesn't have to be like evaluated by an actual computer. Whereas an informal proof is done by humans. Translation is done by a compiler in the computer case, and humans. In the informal case, in some sense, you have an objective object when you have a program, because you have some program on some computer that's in memory that you could take some kind of state. Versus, the informal proof is a subjective notion. Formal proof is a 20th century phenomenon. Post Frege, and informal proofs go at least as far back as Euclid. The orientation is meaning like formal proofs are more about constructing syntactically complete terms that satisfy a type, whereas informal proof is more focused on semantics. So leaving details out, being redundant about other details. It's all about communication of ideas to other people with domain expertise or interest. So it's, much more on the semantic side. So formal proofs give you an inference algorithm. Informal proofs, you need domain expertise in order to infer meaning sometimes. So not just anyone can read any paper. But any computer with Agda on it should be able to interpret an Agda program that I write. The verification is done by the programming language designer by designing the programming language in the interactive theorem provers, whereas humans have to do peer-reviewed verification. Formal proofs are unambiguous and informal proofs are often ambiguous. So informal proofs are a specification and a formal proof is an implementation, that's the kind of main way I've been thinking about it. So specification isn't necessarily contain all the information for everything to work, without fail, but it is an instruction set. And a formal proof is a way of going from the instruction set to the thing you're building. So we think of semantics preceding syntax. So like people thought of circles before they had a notion of pi and these formulas to describe circles or geometrically construct them with rulers and compasses. But we also know that the syntax-oriented, syntax orientation is pervasive in the computer science tradition, type theory tradition. Sometimes given an expressive enough type, the programs write themselves, and both syntactic and semantic thinking are necessary in the end, especially for big proofs. And this is the formal abstracts project, which Tom hails. It's like kind of a Hugel, if you're familiar with Haskell, for theorem provers, where you can have a controlled natural language for mathematics that a mathematician isn't allergic to, but also is somehow interpretable by a computer. And one of the things that should be noted is that propositions or theorem statements in natural language are very unambiguous, whereas proofs can be very ambiguous. But like the twin prime conjecture, even, it's kind of, anyone who has any mathematical knowledge will interpret that more or less the same. One more quote before we get into the meat of the grammars, because everyone's here for GF, so I know this is a long intro for that, but when it comes to understanding the power of mathematical language to guide our thought and help us reason well, formal mathematical languages like the ones used by interactive proof assistants provide informative models of informal mathematical language. I'm not going to read the whole quote, but you should, as these slides are available. So syntactic completeness is just one notion that we, determined as the kind of, way of thinking about GF grammars and their approach to this problem of proof and theorem statement translation. So the first notion we have is syntactic completeness, which means that given a natural language expression that a mathematician understands, does the GF grammar emit a well-formed and well-typed expression in the target logic or programming language? Different people have different interpretations of a mathematical statement. So there may be no absolute intention. So maybe syntactic completeness is undecidable or impossible all around, but there are many syntaxes beyond just alpha conversion that are of interest. Let's leave that aside. The details will have to change depending on the tools and machines available. So as we get better machines, maybe we'll have different notions of syntax, or, like Coq has tactics. So that means in some sense we're obscuring the syntactic object for a different syntactic object in a meta language. And then we can also begin with math as developed in an interactive theorem prover when we're designing a grammar based off this criteria. Dual to it is semantic adequacy. So given a well-formed expression in AGDA, for instance, one can ask if the resulting natural language expression generated by GF is semantically adequate. So basically, is it coherent to a fluent speaker? And by fluent, we don't mean fluent in the natural language sense, like a child is fluent in the language that they grow up around, but more so in the informal usage of a mathematician knowing a domain well enough to speak at a kind of linguistic level with another mathematician about that subject. So this kind of borrows from expressive adequacy and logic, which means that if you can have a really small calculus to describe any formula in your logic, and it's in dispute among mathematicians. Maybe certain mathematicians don't understand a proof and never will, or there could also be like arguments that certain proofs are just bad or ugly, or rely on dubious axioms that others, like the excluded middle, some mathematicians may not choose to accept the excluded middle, and so a proof may be controversial in that case. So if something's semantically adequate, if a grammar produces a semantically adequate term, that's kind of like a Turing test for a machine proof translation. So will the mathematician know that it was a computer that produced the proof from a formal statement? That's like a thought experiment I just kind of wrote down. So it depends on historical developments as well, like what is semantically adequate. So things that were semantically incoherent to almost everyone a couple hundred years ago, save maybe Gauss and some of his students, we take for granted, or most mathematicians take for granted today. And so they've kind of internalized some semantic notions that Gauss and them were inventing. So when it happens to an individual, this is called adaptivity, where the grammar of a mathematician changes as new definitions are encountered. So as you learn more mathematics, your grammar capacity, your linguistic capacity changes. But grammar should just be the starting point for mathematical literacy. And there's a lot more than just grammar. And when we design a grammar that's based off this criteria, we should begin with real mathematical text. So this is just a diagram showcasing these. So we have syntactic completeness and semantic adequacy, and we have our three grammars. So maybe this diagram is better to look at after. And then the last dimension is lexicon size. So what kind of coverage do you have? And this is where statistical methods might come into play. Please review Krasmer's talk. So this is just a personal perspective. Maybe it's been covered in different ways during this summer school, but we just have, when we have concrete and abstract syntaxes, the abstract captures more from, more semantic content. So when you're designing a grammar in GF, so it gives you, if you have a bigger abstract syntax, you have more freedom of expression, and I think this is grammatically wrong, so I'll have to change this. But basically, the more abstract syntax you have, though, if you're trying to embed it in PGF, which is the next talk, the harder it'll be from the concrete perspective. Basically if you have a really simple abstract syntax, I guess, then you're going to have a more elaborate concrete schema. So that's what I'm saying here. And maybe it's my belief that this is more feasible for real implementation, because if you end up having thousands of categories in a grammar to capture all this semantic nuance, it's going to be impossible to parse, or too ambiguous, or any number of things. So let's just look at the first, the first grammar in this case study of this domain, and it's from Ronta's Arne's paper in 2011 at the CADE conference, translating between logic and language, what is easy and what is difficult. Application grammars for logical propositions. Yeah, basically he's defining a grammar for types, but expressed in the logical tradition, not the type theoretic one. And he gives some explicit, like kind of, yeah, normal mathematical domains that anyone who's been through grade school knows, like arithmetic and geometry. But it doesn't cover proofs. It uses a core and extended set of categories, so it translates via PGF. So hopefully this serves as kind of a prelude for what PGF can do, which, yeah, you'll see later with Inari's talk, but let's just say that it's a way of translating between semantically coherent and syntactically like representative phrases. So yeah, one idea that I had when I was understanding and working through this grammar and kind of modifying it for my needs was that you can simplify expressions in natural language based off theorems in first order logic. And that also this grammar serves as a basis for other logics and other programming languages based off this logics. So I'm gonna keep talking just through this one grammar and then maybe we can take a 5-minute break. Or maybe not a 5-minute break, but like a 2-minute break. So the logic grammar is kind of the minimal amount of necessary expressiveness, but it is syntactically complete. So the core grammar, and yeah, the more conjunctions you have this greater than exponential explosion of parses called the catalan number. So the expressions in the core syntax are often unreadable or illegible to a human. So here's an example. If for all x, if x is a natural number, then x is even or odd. So that's spelled out very explicitly in this sentence, but it doesn't sound very natural. But it is syntactically fully expressive of what the formula means. And a semantically inadequate example from this core syntax would be something like, it is the case that the sum of 3 and the sum of 4 and 10 is prime and 9,999 is odd. But that sentence probably didn't make any sense to you. And in order to parse that, you would probably need to work through it with a pen and paper, especially if there was any more kind of run-on sentences or run-on expression data. So here's the core syntax. It's basically just the same syntax I showed earlier with the natural language way of expressing it. The extended syntax is much more expressive. So based off our criteria, it's semantically adequate. It increases both the number of categories and functions and therefore, yeah, it also has more complicated linearization data that you need to keep track of. And the PGF background is complicated in order to translate between the two for syntactic completeness. So there's questions about how much you can extend grammars at scale. But you can see that the same formal expression comes out to how you or I might say it to a stranger. Every natural number is even or odd. And this is the various things that the different abstract functions in this grammar capture that are kind of yeah, just window dressing in some sense, but also not, because if you want to talk about things logically to a logician or mathematician, you're going to use these kind of more natural sounding phrases. So you have lists of propositions, predicates, variables, negation. Instead of saying it is not the case, you say X is not even. Yeah, you have this in situ quantification, which is a focus of Montague. So, but it exists in mathematical language as well, etc. So the details maybe better be left to the paper if you want to look through the grammar yourself. And I guess the whole idea is that you're translating between them via PGF. So from extended to core, it's what's called denotational semantics. So it's deterministic algorithm. It's relatively simple. I mean, it's not going to be like a 1 hour exercise to do it, but if you have a decent Haskell knowledge, you can probably figure it out in a couple weeks or less. And yeah, you basically want to see the core syntax as a model for the extended syntax. So if you're talking model theory from logic. Back the other direction. So I don't know if I should have the semantic brackets here, but to go from core to extended, it's a difficult problem. Yeah, it's infeasible at scale, because how do you choose the best way, most concise, most clear way of expressing something? A big formal term, say some complicated AGDA term. And you kind of obscure some detail when you go this direction, but in some sense it gives you more intuition as to what you're actually talking about. So here are just some of these conversions that get worked through in the PGF layer. So you can take a phrase like X and Y and Z and turn it into a list. Also aggregate the predicates of a variable if it has multiple predicates that it obeys. So you can say for all X, blah, blah, blah. You could just say everything in natural numbers is even or odd is missing here. Yeah, negation we saw earlier, reflexivitization and modification. So basically, yeah, how do you come up with linguistically nuanced ways of saying things that, when spelled out in excruciating detail, may obscure their meaning? So maybe I can take like a 5-minute or a 3-minute break or something. Is that cool, Inari, or do you want to? All right, well, maybe, hello?
Yes, let's take a 5-minute break. So resume 10 past 10.
All right. Are you ready?
Hi. Yeah, let's wait for 1 more minute. Yeah, I just wrote some comments in the chat. Like the comment about like, oh, I'm only getting this when I do this. Like, I didn't mean to say that, oh, you must have forgotten that flag. That was just commented. I never run into that with an application kernel, so I'm curious to see what.
Okay. No, I mean, maybe I was speculating too much. I mean, yeah, there's probably a good amount of criticism that.
Yeah, I mean, I was just like, yeah, if you, yeah, we can talk about it also offline. But,
Yeah.
okay, so it's 10 past. So.
We're working programming.
Oh, okay, right. Yeah, one from the classroom went to get coffee, so maybe we can. Or I think, I mean, we have people on Zoom. Let's just get started, so she can join later. Yeah. Okay, so go ahead.
So this next grammar is from 2014 by Arne at the Stockholm University mathematics seminar called Translating Homotopy Type Theory and Grammatical Framework. So he took a real piece of mathematics text and kind of it served as a case study for how do you implement a grammar that produces this text verbatim. So there's no PGF in this grammar. It's just a pretty large abstract syntax. It has LaTeX support, meta document structure, and it has a hot specific lexicon, homotopy type theory, hot. It includes proofs, but the abstract syntax trees are not similar to those of terms in a programming language because they're kind of accommodating certain natural language phenomenon that you don't need to in a programming language. So it distinguishes between expressions and propositions, and in some sense breaks the Curry-Howard correspondence in doing so. So it makes it hard to translate to a programming language like Agda. So we will say this is a semantically adequate grammar because it covers real world text, but it's syntactically incomplete. It's hard to figure out, okay, how would you translate, how would you write a linearization to a programming language such that it's unambiguous and compiles or type checks. So this is the library structure. So these are the abstract sides. So you have a lexicon on top of a framework on top of a set of formulas. So in some sense, this is where the logic grammar lies. This is where a lot of the syntactic nuance as well as the document structure and LaTeX lie. Or I guess the LaTeX is referencing the formulas. So more of the document structure and then the lexicon on top of that. So this is some Pigeon logic language that Arne just produced ad hocly. And then there's English, but there's also a functor. So then you could actually, there's multiple, I think there's French and maybe Swedish or something. So these are just all the categories, which shows that it's, yeah, not a trivial domain in some sense. That a lot of these categories might confuse you because you're like, well, what is a sort versus a proposition versus a predicate versus an expression? These are the formulas. And things like universal phrase, which in some sense, yeah, doesn't need to be covered as a separate category in the programming language side of things. But from a linguistic perspective, it makes it easier just to add a new category for that. So this is just kind of a case study. we look at now 2 examples of statements from like homotopy type theory. So this is just rendered LaTeX definition. I modified Arne's grammar to make it compatible with this cubical TT language. And then this is actual AGDA code that type checks, because AGDA code gives you coloring when it type checks. So we say a type A is contractible. Sorry, we say a type A is contractible if there's an element A and A called the center of contraction, such that for all X and A and X are equal, and this means that they're a path. So basically the whole space is path connected. And can be compressed to a single point. And this is how you say it in cubical TT. So you say that it's a predicate to say a type is contractible. So you say it's a mapping from sets to sets. And given any, yeah, it's basically the property that you have an element of A, and this is the sigma notation, or it's just a dependent pair. So you can say, and a proof that for any A and A, it's equal to X. And this is a more classy looking AGDA version of that. So I'm just offering this as an example where you want to kind of deconstruct your domain and look at these different syntaxes. So both these top 2 are produced by the grammar. The bottom one is where you would want to take this second one to the third via some post-processing or some other GF layer. So here's a different case of definition that says an equivalence, which is more or less a way of thinking about bijection in a more modern sense. But there's an error in this. So the error is in the logical or pigeon programming language syntax. So we say a map is an equivalence if every point for all points in that codomain, the preimage over the map is contractible, or we can also say that 2 types are equivalent if there exists a map between them that satisfies this property. So again, equivalence is just a predicate. And this is the AGDA code versus the pigeon wannabe AGDA code. But you can see that how Arne dealt with it, meaning the anaphoric its fiber, isn't able to be simply resolved. So the fiber it, the fiber should be, it's it to set. So it's not, and the it isn't referenced in this function body at all. So you can see that the AGDA one that type checks, like there's no way of feasibly writing a post processor that I can see that would turn this equivalence into this equivalence. So either I didn't notice some details when trying to produce this expression, and maybe it's my oversight, but it's clearly difficult to produce a syntactically complete expression from this semantically complete natural language LaTeX rendered definition up here. That's the point, is that to go from this direction to this direction in this grammar is very challenging already. And it's even more challenging when you have theorems and proofs that have any length or substance. So that's my kind of summary of the hot grammar and what I took away from it, at least what I can express very quickly to you now. So let's just say the last grammar is the perspective that we just want to use GF as a programming language parser. So in the same way that you write a parser for any programming language, just use GF as that tool. And the only question is, how do you do that such that it linearizes to natural language in a semantically meaningful way? So because you're taking the PL perspective, it's already syntactically adequate if you're basing it off a real programming language. All the precedence information, so the binding of, like, for instance, multiplication and addition. So if you want to have a tree without parentheses, or if you want to have a string without parentheses that maps to a tree that has the times at a higher precedence than the plus, then you do that with the concrete syntax in this case, because that's how you eliminate ambiguity. So yeah, there exists a lot of programs to test this on, because we're using, in this case, we're using cubicle TT, which I have a different slide, but I don't have it here. So just a prior note, in a dependently typed language, basically you're compressing both terms and types into like a single syntactic expression unit. So distinguishing between them is difficult or kind of vague. Whereas in like a simply typed lambda calculus, you have different sorts from the get-go, or different categories in your GF grammar. So it makes it easy to write an abstract syntax for the programming language, but if you want to have syntactic nuance, it's difficult to linearize it to a natural language that's, yeah, semantically coherent. But also, just a side note, that just because I said it's easy to write an abstract syntax for GF or programming language, or at least a simple one, that it may not be actually easy to difficult to implement a parser in a real, for a real proof assistant based off dependent type theory. So Agda's parser is, like, as I've been told, like 4.5 unique kind of stages where you have type checking in between the parsing. And maybe if we have time, which I don't think there will be, but to look at some Agda code in like an interactive environment, you can see that there's a lot going on behind the scenes, and that, yeah, parsing in a dependently typed setting is actually a really hard problem if you're trying to implement a nice programming language. So in this grammar, so first we have a, yeah, really basic. So I'm going to show you two. So I'm just going to show you a basic dependently typed programming language, and then I'm going to show you one that's like more geared towards homotopy type theory. So yeah, I think I had forgot that detail when I said something in the last slide, but all we have is expressions, variables, telescopes, which are basically ways of saying, like, basically ways of doing quantification, and or L is for lambda. So if you have a lambda expression with multiple, yeah, if you want to have lambda x, lambda y, lambda z, etc., then you can, instead of having 3 lambdas in a row, you can say lambda x, comma y, comma z. So that's why these are the list categories. I don't know if you covered list, but you can unfold a list declaration to a category, which is just desugared, and 2 functions with the base case having n, n categories. So the list is, yeah, you're presumed to have the variable before you introduce the list. I have no idea if that's redundant, but it's good to see again. So this is just the abstract syntax. So here I kind of, even though everything's an expression, I distinguish between the types and the terms in how I design this language in GF. So you have your arrow type, your pi type, which is the for all, or for every in mathematics. You have your identity type. And the reason I put this here with two different ones with just a different arity, one, this has 2 arguments, this has 3. So maybe this should be id3, but is that Agda's type inference allows you to oftentimes get away with not. This first expression is meant to signify the type. So when you have earlier, like P or X equals Y, and the equal has the subset or the, is restricted to the A, then that A can often be inferred by the type checker. But for the natural language people, sometimes they'll express, if it's ambiguous or seems more relevant, sometimes they'll express the type and sometimes not. Then you have your lambda calculus, where you have variables, lambda expressions, and application. This is for the identity type, you have just a single constructor and a way of eliminating from it. So this is like a proof by induction. And then you have your natural numbers. So you have 0, successor. You have a eta expanded successor. So sometimes you can just write suck in Agda without giving it an argument. And you also have the natural number induction principle and or proof by induction. So here's some Agda code where we show how to define the natural numbers. So, and equality. So you say that data keyword, this says we're defining an inductive type where the formation rule is just says that the natural numbers are a set. The constructors or introduction rules say that 0 is natural and successor is recursively takes a natural number to a natural number. The equality type has all this data, so it's polymorphic over the universe. So you can say, you can define equality over any type, and given any expression or any member of that type, then you can produce a type that is basically a predicate over the type. And so then you just have one constructor that says that actually the only thing you can have is that something is equal to itself. So this kind of goes back to why it's confusing, where you can write X equals Y in homotopy type theory. So, sorry, I'm just looking at the time. This is definitely taking longer than I thought. 2 is defined as just the successor applied twice. So you can say a double function by pattern matching. So double of 0 is 0. And if you have a successor, you just apply the successor twice and apply it recursively. And then 4 is equal to double 2. You define addition by recursion after you deconstruct the first argument into its constructors. And this theorem right here says 2 plus 2 equals 4. So in Agda, oh yeah, that's one thing, is that you have Unicode in Agda. So it looks a lot prettier than your typical programming language. And all the colors mean that it type checks. So basically that the programs are supposed to do what you're thinking they're doing. And this just says that reflexivity proves that 2 plus 2 equals 4. And not just that, but that there's no other data here. So that means that this propositional equality is actually also a definitional equality. There's the Agda computes based off the definition of plus that 2 plus 2 actually just evaluates to the successor function applied 4 times. So let's just look at a associativity proof from this famous book about Kalk called Software Foundations. So it says for any n, m, and p, and this is a very pedantic proof that a mathematician might not write, but is interesting if you just want to teach a student a formal proof or use it as a case study like we're doing. So you just say that they're associative if you can basically reapply the parentheses in any order. And you do it by induction. So if the first argument is 0, then this follows directly from the definition, means that it's definitionally equal, this expression, that the programming language can actually just evaluate that and say that they're equal for you. In the successor case, you have to apply some lemma in between that says that you can move the successor from one place in the expression to the other. And then once you have the successor, then you know that these two things are equal by the induction hypothesis. And so you can apply the successor to both sides. And yeah, so the first we'll look at the pattern matching proof in AGDA, just to kind of compare it. So in the 0 case, you just have the definitional equality. So this, you don't use the for all symbol, you just use this, you just use the parentheses to bind the variable the variables mn and p to n, and that means that it's a pi type. So this is where the propositions as types comes into play, that you say associativity plus has the type of taking 3 numbers and producing a proposition of their equality under some juggling of parentheses. And the application function just says what happens in the last step of this proof is that you apply the induction hypothesis here, and then you apply the successor to both sides. So if you have two things that are equal and you have a function over the space that they're equal on, then you can say that their images are equal in the codomain B. So yeah, this is how the proof goes in kind of vanilla AGDA, is that you just apply this apply function. So the F here is the successor. The equality proof is the recursive call of associativity on the M, N, and P. So the M is, you're getting rid of a successor. And so the termination checker is what it's called, is happy, because the size of the arguments is in some sense decreasing. And so, it'll terminate recursively. So you could instead define a proof by induction in AGDA. So you can say a proof by induction is really a predicate, which given any number gives you a type or a set. And then if you can prove that predicate true, so that predicate is just the property that you're trying to prove about the natural number in question. If you can say it's true for the 0 case, and if for any n, given the predicate holding for the n case, you can prove that it holds for the successor case. So given, if we assume something's true for n and we can prove it for n plus 1, then we can say it's true for all numbers n, the predicate is. And this, you just derive this induction proof principle from the pattern matching. So you have your base case, your step case, and the thing that you're inducting over, and you just apply the step function or the inductive hypothesis to the reduced size number and the inductive call. And this is the proof in AGDA that's meant to target or look exactly like the software foundations proof. So let's just rewind. So you induction first on the 0 case, by definition, successor case, and then you apply some lemma at some point and apply the induction hypothesis. So here we say, given 3 arguments, we apply the natural number induction principle we just derived. So we say the base case and the inductive case applied to the first argument m. So the base case is just one of these definitional qualities. It's just equal to ruffle. Agda does the work for us in the induction step. Yeah, it's kind of instructive to look at these side by side. So maybe this isn't that informative if you've never seen Agda before, because it's too much to look at it once. But just notice the kind of overall form of a base case and inductive step. And this here is just kind of a, I just included it so that it would resemble the other proof, but realistically it's not necessary because it overcomplicates the proof term. So this is the proof in, yeah, the dependently typed syntax that we choose. So you can see the parse. I use lhask for here, so it's some kind of like Haskell wannabe looking syntax or whatever. And you can see it's just an ugly kind of looking version of, well, I guess it would be an ugly looking version. I wrote another proof that looks more like this, but yeah, maybe it's not too instructive to look at it because it's not a very nice syntax, but this is the Pigeon natural language associativity proof. And I started refactoring this to be compatible with the RGL, but it's not yet complete. So this is like a really ugly proof where it's not using pre-RGL, but it kind of looks like, okay, it's like a working example of something that might be translated after a few weeks or whatever into something like this. But you can see there's some really ugly, so you're explicitly using the applies of the lambda calculus. So you say apply plus to f to apply plus to y. So this is completely illegible to a native speaker. So this grammar that I've written, it parses this, so it's syntactically complete, but this is semantically incoherent, although it has the makings of, or it has a promising future if some, yeah, blood, sweat, and tears are put into it. So there's just one last grammar, which I'll just talk about quickly. So how can we build a GF programming language parser that unambiguously parses? Yeah, so I kind of am recapitulating something. So I took, yeah, there's this homotopy type theory book, which is like a canonical source for learning HOT, written by many authors. It was formalized while it was written in LaTeX. So there's kind of parallel corpus to look at. It's open source, and the many authors aspects means the language, the natural language is neutral, or certain things are written by certain people. So you kind of get a good sampling. So I wrote a custom Agda library, which is in some sense both ready and not ready for the public, but it's meant to like be an exact Agda transliteration of the natural language proofs from the hot book, because the Agda and Coq libraries, even though they correspond to the text, are not equivalent in any kind of way. They, yeah, they may like rearrange orders, or they may use unmentioned lemmas and or other abstractions that the book doesn't mention. So that's why I wrote this custom library, but I haven't actually had a chance or had time to test it with the grammar, because obviously this syntax is not good. So yeah, what is cubicle TT? I mean, it's basically, there's a lot to unpack here, and obviously this is like very experimental research. So the whole idea is that you have this computational interpretation of homotopy type theory. So the distinguishing between propositional and definitional equality is kind of reduced into just understanding one equality. So there's something called cubical agda, which was preceded by a different proof assistant called cubical TT in Yotobori. And there's this parser generator called BNFC that's a cousin of GF, which is just meant for programming languages. And so I'm just saying here that these 3 lines are how you define this in BNFC, the lambda calculus. So you take, and it mimics the kind of Chomsky whatever syntax for including strings. So so in GF you separate the abstract and the concrete, and BNFC you just keep them all in the same, all in the same file. So the quotes here are obviously strings, and this is the abstract detail. But the precedences are natively treated by BNFC, so it's easier to prototype programming languages. But it's a pretty straightforward algorithm to go from BNFC grammar to a GF grammar. And this is using this library from the RGL, these infix and mcprec and useprec operators. So let's just look at an example that from this library that I designed but didn't get to test. This is in some sense, how you do proof by induction with this propositional equality. And this is how you prove that if you have a path, so if you can get from X to Y, then you can get from Y to X. Paths are reversible. You can walk backwards in some sense is what this is saying. And I'll leave this for you to read on your own time, but this is the actual text from the hot book. So maybe the proof is too complicated to look at, but all it says is for every type and 2 points in that type, there's a function between the path in one direction and the path in the reverse direction. This gives some syntactic information. And this isn't kind of a part of the definition. There's no REFL inverse when you define this type here. It's much simpler to look at the type in AGDA than how they put it in this lemma, but this is being very explicit to kind of showcase how homotopy type theory is done, or how it was originally conceived. So yeah, and it gives a difference between the verbal and the symbolic. So the symbolic is the inverse 1, or the minus to the power minus 1, versus the inverse is the verbal expression of inverse. So I think I've got like a ton of things in the to-do section. So basically saying why natural language generation is hard, why programming language generation is hard with GF, what mathematicians might object to in using proof assistance, and what a computer scientist might be frustrated when trying to read natural language. So I'm going to just omit the content of these slides and just kind of say that these are a lot of thoughts that I've had ex post facto, doing a lot of work and not getting as much progress as I wanted. So maybe this is a good slide to just look at. So how will the foundations of mathematics change, and how will this change reflect new ways of speaking? So how can foundational changes affect our linguistic perspective? What is GF's role in this problem? And what are the obstacles or limitations, and helping solve this problem of proof translation, higher inductive types, like ways of constructing spaces, and homotopy type theory give, in some sense, greater intuition than the classical mathematical constructions. So how will these affect changes in the programming language computer, or the programming language community that's dealing with mathematical proofs? And yeah, this is more of a really open-ended question. What about graphical proofs and graphical programming languages? So there's a good Stack Overflow question about graphical proofs that you can see, like proofs where there's no verbal syntax, but it somehow demonstrates the validity of some theorem. And that's something that our grammars don't cover, or most there's no like theory of proof from a graphical language, from like a formal languages perspective, as far as I'm aware. And there's also graphical programming languages where you can drag and drop boxes and wires between boxes, and those somehow generate something. So how will that affect, the domain of mathematics and doing mathematics with programming languages, opening it up to a general audience, etc. Future work. We want to kind of combine all three grammars, or I guess I showed you 4 grammars, but RNA's 2 grammars and my approach using a programming language grammar into a master grammar, let's say, and see how that can capture both semantic adequacy and syntactic completeness. More linguistic analysis is needed. And Krasimir was saying how the bigger a grammar becomes, the more it begins to resemble a resource grammar. So maybe we should just build a resource grammar for programming languages or formal languages in GF. A to-do that, won't have time to discuss. Related work, also references. I don't have citations on the slides because I don't have time, but you can look up any of these words. It's all interesting. One thing to say is there's a machine learning approach where you can train data on multiple corpuses, but I reserve some skepticism, although I think there's a lot of promise. In some ways, there's also a lot of obstacles into using statistics just to translate mathematics, and it seems infeasible in a lot of ways. But some people are not as timid as me. So I'll just conclude with this metaphor. So we've covered a lot of ground here. Maybe this is too much to cover in a single talk. I hope not, but any feedback into how much was comprehensible to people either with expertise or without expertise in any of the things I was saying is welcome. So I think that one way of thinking math is it's like a religion, and you can ask questions about the philosophy or foundations of maths and say, like certain people have different perspectives and they're going to evangelize those perspectives because that's what they know and that's how they think about the world. But there's also a lot of forks, reinterpretations of scripture, heretics, etc. So maybe that's a little bit cynical to claim something like that. But in some sense, this is actually a very tangible problem of using GF as a proof translation engine. And that instead of viewing this as like religions where everyone's out to like convert the world and out-compete each other in converting the world, it's like maybe we should just see the mathematician as the architect, where they have kind of the aesthetic, the specification. They're dealing with what the end user of a building is actually going to see, let's say a structural architect. And then there's the engineer, the structural engineer is the type theorist who actually implements the details of that blueprint that the architect gives them. And there's many ways to, implement. You could use different types of steel or different, whatever, like style of window or, different structural foundations to build a building depending on whatever the soil conditions, etc. And then this is really a question is like, where does the linguist lie in this from like the GF subset linguist perspective? So maybe the linguist is kind of the scientist who it's like there to look at empirical data and hopefully feed both the type theorist and the mathematician some interesting perspectives that they can use to inform what they do going forward. So I'll leave it at that. I'm sorry that was really long, but apparently it was, I'll have to cut that in half for my thesis. I hope that was comprehensible.
Yeah, so I will just give the first one of my talks. So like, I'm not gonna cram 2 talks into 1 hour. So let's give feedback for you, and then we go on a break, and then I'll give my 1 talk. So I've written my feedback in the chat. You can look at it. Anyone else have something to say?
So hi, yeah.
Let me turn off. Let me turn off.
Hey.
Yeah, okay, there's no more echo. Yes, thanks for the talk. Was really a large overview talk. I have one remark or question. So I remember that people were doing sort of proof extraction from resolution proofs years back. So in the, well, 1990s, 2000 maybe. So that was work done in Saarbrücken. So they took, well, resolution proofs, and I think they tried to convert them into natural deduction proofs. And one could say that natural deduction proofs are not so far away from, well, let's say, yeah, type theoretic proofs. Yeah. So many proofs that are carried out are, in fact, one could say, intuitionistic proofs, even if they are done with resolution style theorem provers. And they tried to convert those, well, they wanted to have several representations of these proofs. And they, well, first converted resolution proofs into natural deduction proofs. And then they tried to convert these natural deduction proofs into natural language text. I do not know whether you've looked at that, but that may be interesting. Yeah. So they had all the kinds of problems that you alluded to, like, well, sort of dealing with lemmas, for example, or referring to parts of previous proofs and so forth. Yeah.
Mm-hmm.
So that may be interesting. So I just wonder what is, yeah. So whether one cannot sort of factor out common problems of yes, converting proofs into natural language, and that are relatively independent of the logical framework, of the underlying logical framework.
Yeah, I mean, I think I don't know anything about this specific research, but I think that there would be like a good place for a kind of survey paper in this space to kind of go over all these different attempts at proof translation, and yeah, like Boxer and Approach and Mizar and the statistical methods and whatever your resolution to natural deduction method was called, or I don't know if there's a specific system underlying it, but I don't have any specific comments other than I think that a survey paper would be of great interest because, yeah, clearly a lot of people have been digging at the mountain from different places. And I think there's, yeah, some need to figure out what have all these people, what are the common, yeah, pitfalls, and also maybe what are some things that are easy in one system or difficult in another system. So I hope that's a fair response to your comment.
Any other questions, comments, both on the the content, or as you were asking for feedback also on the presentation. So if you have any of those, you can also say that.
Yeah. You can also just email me your feedback. If it's more elaborate than time permits now.
Okay, so
So I can so I can rephrase my question. So what is specific about type theory if you want to convert, let's say, mathematical text or mathematical proofs into natural language? Yeah. So I wonder whether there's not a common, sort of something in that several mathematical representations have in common that you can factor out, and whether this is not the main difficulty, let's say, and whether you use type theory or homotopy type theory, whether that makes a huge difference. So that is something that I did not quite understand in your talk. Yeah. So what is specific, or why do you consider type theory or homotopy type theory and not, let's say, general natural deduction style proofs, for example?
Yeah. I think that's a very fair question, and maybe it's just one that reflects my own interests. Like, my background was in mathematics, and part of my draw to type theory was like learning about homotopy type theory. And also, I guess, being in Yotobori, like with Agda being kind of a central tool being produced at Chalmers, that's also a big, maybe it's just the school of thought or tradition that I'm coming from, rather than any, methodical reason of choosing, this flavor of type theory or homotopy type theory. But I mean, I guess, I think that a lot of people, or at least some people, are convinced that homotopy type theory and cubical type theory are the future of mathematics. And there's a lot of reluctance, and that's maybe still a very controversial opinion to take. But if one does entertain that possibility, then I guess that would give this style of proof or this foundation more precedence. But obviously, like I said, it's very controversial. So maybe that's only going to find a small audience to, accept the premise.
Any more comments, anyone? If not, let's take a 10-minute break, and then I will introduce you. I'll give you introduction to the internals of GF. So like the PGF in my talk, that's referring to the actual format, not to the Haskell library. So just in case someone's confused about that. So let's resume 11:08. And thanks for your talk, Warrick. You may go to sleep if you want to, or you can.
Yeah. I'm gonna go to a bar and then go to sleep.
Now grab a beer and listen to how we compile GF to the.
Otherwise, my dreams are gonna be too.
You were talking in your presentation about also, like, you expressed this concerns about if the PGF, like the low-level format, how it will grow up. So if you listen to this talk, then you'll know.
All right, cool.
Okay, so let's resume. Okay, now it's 9 past. 9 past.
Yeah. Oh my God.
Hello. The people are still out there having coffee, but I should fetch them back. Yeah, can you get them back there? Oh, more dense talks about low-level details. That's what we need for this morning. Now this talk is about vegan pizza. Nothing dense about that. People are still having coffee. Okay, right. Yes, so this talk is about the internals of GF. Oh, sorry, there was something on the chat. Let's see. Question: does the pizza have vegan cheese? We'll see. We'll see. Well, so, yeah. So internals of GF. So we have. This is the. If you've been following in the summer school or for the past 20 years, this is the kind of. That's the kind of way you're seeing GF. We have a fragment of the foods grammar, and specifically the part about modification. And this concrete syntax is for basically any major Romance language, like, or it could be many different ones, but I'll use Spanish in the later examples. So the kind has an inflection table for a number of string and an inherent gender, and the quality inflects in both number and gender. And then it has also an inherent parameter for whether it comes before or after the kind. And then in the modification function, we just determine the word order and the right agreement of the adjective. So that's what we've seen. And now we're going to talk about the lower level function. So after this talk, you will know all about what these things mean. So do you need to know the internals of GF? If you're here, you probably want to use GF in some way. And so maybe we can ask a similar question that someone has asked. So do you need to speak Italian to eat a pizza? That's probably not. You can enjoy a pizza perfectly fine, even if you don't speak Italian. So how about then do you need to know the internals if you want to write resource grammars? So maybe the corresponding question would then be, do you need to speak Italian to make a pizza, like a really good pizza? So there are some scenarios, like sometimes you have ordered a really good pizza oven straight from Italy, but then if the pizza oven overheats and you have the instruction manual only in Italian, then you need to read it, otherwise it's screwed. Or maybe you have ambitions, like you don't just want to make pizza, you want to become the pizza oven maintainer, then certainly. Or you can maybe you just love pizza so much that you want to learn everything about pizza. So then that's this sort of natural association to also learn to speak Italian. So yeah, you may have your motivations, but I'm gonna present. If you're following this, I assume that you want to learn about it. So I will present how we compile GF to the low-level format PMCFG, parallel multiple context free grammar, in the concrete format of PGF, the portable grammar format. So here's the example which I already. Sorry. Oh, okay, sorry. Sorry, I have the Zoom thingy blocking the view. Let me move it. Is it still blocking? Okay, great. Sorry about the distraction. So this is the example I just showed. We have the inflection table from number string, inherent gender, and the quality has the corresponding its variable on gender, and then it has an inherent feature whether it's pre or post. So where do we start the compilation? In the PMCFG level, in the PGF, we don't have anything as fancy as tables. So these two categories will become concrete categories. Although they are not at all named as nicely as kind and quality. They're named like C5, C6, C7, C8. So what happens? We have the inherent parameters. So these will be, we will have now one concrete category for each combination of inherent parameters. So in this case, there is no combination, there is just one of them. So both of them become two concrete categories. One for, like here you can see C5 corresponds to the kind where the gender is masculine, and C6 corresponds to the kind where the gender is feminine. And vice versa, like also like this would be, I don't know, one of them is the quality where it's inherently pre-post, and one of them is where it's post-post. So that's the parameters. And then we have also the table. And the tables, we can't have them either in the low-level format, so they just flatten into something called labels. So in this quality, we have, it's a nested table, but in the concrete category, it's just flattened, like we just spell out everything like that. If you have questions at any time, just feel free to ask. So what do we do with these categories? So there is the next layer is the production. So if you're familiar with any other kinds of grammar formalisms, like, just context-free grammars, like anything you've seen, this is like pretty much the same idea, that we can form a category C5 by applying F27 to C7 and C5. If you're wondering about the syntax, like this is, here's like this is how you should read the F27. Like it's basically a function that is applied to another C7 and C5. So if you think of in a context-free grammar, of course, you could not have a function on the right-hand side. You would just have terminals and non-terminals. But since we are much more powerful than context-free grammars, we can have a function on the right-hand side of the fraction. So yeah, that's how we apply F27 to C7 and C5, just like it's spelled out here. So what do these functions contain? So these are now concrete functions. So we come back to the mod. This is actually, I think, yeah, this is straight from a dump that you can get with the GF shell if you just give it the right flags. But I have manually inserted these post-mask, pre-mask myself, because like the compiler doesn't give that information anymore. I just look at the PGF to determine which one it was. So, right, so now the mod, we remember that the, here we can see it. It takes a quality, a kind, and returns a kind. And because quality and kind each compile down to two concrete categories, then this concrete function, which takes one of each, it compiles to the combination of concrete categories. So now we have 4. And as I have written here, it's because in the GF grammar, we just wrote one function called mod, which it used some higher level constructs like case blah, like case expressions, like it pattern matched an internal parameter, an inherent parameter with both quality and kind. But in this case, like the concrete functions are much simpler. There is like they don't know about pattern matching. So instead, we have one concrete function that takes a post modifier at post modifier quality and masculine kind, and another one that takes pre-modifier quality and masculine kind, and so on. So they can do one thing. They can only do one thing, and they just do that. They don't know about any high level constructs. So how do they do that? We look at these. What are these S's that are on the right-hand side of these concrete functions? They are called sequences. And sequences look like this. Sorry, let me remove the annotations. Oh, sorry. Clear the annotations. So what's a sequence? So they define the actual action that happens to the arguments. So like this looks like nothing like GF syntax anymore. Like this is extremely primitive. So okay, let's take an example. So pizza. Okay, pizza is simple. It's just the strings pizza and pizzas. So previously we renamed pizza into F31, like we can see on the top corner. And that pizza is defined as a tuple of these 2 sequences. And like that tuple also has the labels SSG because it's an S field, and the S field is a table that is accessed. You can access that string with this param SG. So, but I mean, in this level, we don't even have the labels. It's just these sequences. So, but the order is significant here. So, right, F31, i.e. pizza, is a sequence, is a tuple of sequences, pizza and pizzas in that order. So we have resolved pizza as far as we can. And then, okay, so what about the others? Like we have all these weird numbers here. So this kind of like angle bracket n comma m, it means the first one is the argument, like the number of the argument, and the second one is the number of the string in that argument. So examples follow soon. Yeah, let's zoom in to one of those concrete functions here. So this F29 used to be the mod that takes a post modifier quality and feminine kind. And so if we remember from a couple of slides back, quality has 4 strings in it because it comes from a nested inflection table. So it's both the gender and the number. And kind has 2 strings, just like we saw in pizzas. And what does, so S23, 1.0, 0.2, so it builds a new string. It takes the first string of its second argument and the third string of its first argument. This is very confusing. So example. Okay, sorry. No, let's just look at one of them. And here is the example. So this is now post modifier quality feminine kind. And now this is the singular version. We know it's singular because it's in the first field of the tuple in this definition of the concrete function. Okay, so what does it do? Right, so So it's zero indexed. So this means pick the first string of the second argument and pick the third string of the first argument. So now you should be able to predict which ones will be chosen. It's going to be, the first one is going to be pizza, because that comes from the second argument, because mod, you can see the type of mod right here up in the corner. So the first argument is quality, and the second argument is kind. But in the string that we produce, we actually start with the kind, because it's a post modifier quality. So it's completely fine to go against the abstract syntax. I mean, I wouldn't even say that we go against anything, because we just have to have some arbitrary argument order, and then this low-level PMCFG is the one that actually decides the string, the ordering of the arguments in the string. So this will become pizza vegana. People on Zoom, I'm just walking around showing the right, I can point the camera like this. So that's, and again, we put that into this first field of the tuple in this concrete function, because that concrete function returns a kind, and kind has two fields. So this is how we construct the singular version of vegan pizza. And now the plural version of vegan pizza. It's the next thing. So it starts, so just like the singular one, one. So like it starts with the second argument, and it starts with the second argument. But now the one that we choose, like in the singular version, we chose the first one, which is the pizza. This one now we choose the second one, which is pizzas. And again, it still puts the adjective for the quality after it, but now it's choosing choosing the fourth one from the quality. So that's how we get pizzas veganas, right? So that's what happens that's in a nutshell, like that's what happens, like that's how the low level thing works. So recap, or actually any questions before this?
One of the earliest slides where we have numbers, can we go back to this one?
Like this? This?
I think one more. Yeah, if we look at the transparent area, the number, gender, string. At the top, the quality.
Oh yeah.
And then at the bottom, the quality is gender, number, instead of number, gender. Does it? Is it because it really doesn't matter I put gender first or number first, but somehow at the low level when it comes to quality, I just put the gender first, then the numbers.
Oh, I guess like in the low level, like I might have made some mistake when I annotated these things, but like in the low level, it's like just we don't even care like what, like we don't actually retain the information, which one was number, which one was gender. It's just the order is the one that matters. So we always know that when we have a thing like the arguments look like this, so then it's always in this order, and the sequences work in like assuming that things will turn up in that order.
So in the perfect world, we will have quality first and kind. So our first.
Yeah, I mean, it's nothing about perfect world or imperfect. Like it's just like in this case, like all of these exist. So let's look at this slide. So these are the pre ones. So we can see that like, okay, these are post modifier mods. So it means that we put the kind first. these two are pre-modifier mods. So we start with the quality because this first number is 0. And then we put the kind afterwards.
Okay, so long as they are annotated somewhere. Okay, it doesn't matter. Okay.
Yeah, it's like that PGF file just like contains that mapping somewhere. That like, okay, so this is how it corresponds to. So yeah, so I'm not gonna. I have some time. So this was the shorter of my 2 talks, but I'm not gonna give you the full second talk. But I'm gonna give you like super brief overview. Okay. So the recap is just here. So just to remember what all the things we just went through. So GF grammar has an abstract syntax, then a concrete syntax, and now the categories flatten to concrete categories. The functions become productions, just like which look just like in context-free grammars, except that right-hand side may contain functions. And then these concrete functions that are on the right-hand side of productions, they resolve into sequences. Like these sequences are the machinery that actually puts together strings, like pizza vegana, pizzas veganas. And right, oh, that was it. So, so if you want to learn more after this 20-minute introduction, depending on the level of detail that you want to learn about, you can read a couple of PhD theses, or you can read a blog post where I talk more about things, including variants and that kind of stuff, which I didn't cover here. The links, these slides will also be in the repo, so you can just click the links. So, right. And no questions on chat. So originally, when I wrote, like, so this started as a blog post, and the second talk started also as a blog post, and from why I am interested. So like, if you want to ask, why am I interested in learning Italian, or rather, like, why do I need to know? Why do I want to know about these sequences and concrete categories and stuff? Because on Tuesday I spent like an hour talking about morphosyntax, and that's, if I like morphosyntax, why do I also like this? And so the question is that, because I want to write resource grammars, and it's often the case that resource grammars are very, very slow. And then if you know this level, you can kind of use that knowledge to do some clever hacks, or even like, not even hacks, just like design choices. Like if you know, for instance, that, okay, parameters are expensive, but strings are cheap. Maybe that's like a rule of thumb, and then you inspect this low-level stuff for like 5 grammars, and then like, oh, actually parameters are okay in this context, and like that kind of stuff. So instead of going through my whole talk, let me just I'll stop sharing and go to my blog. Yeah, perfect. So if you know me, like if you ask a question from me, that's the place I direct people to. So right, so that first talk is this one. This is the one important part I didn't cover in the talk. It's pretty interesting, but it's also pretty long. So how do I go to the previous page? I'm using Chrome because I don't know how to use full screen in other browsers. And then, so the other post that is the follow-up, not sure follow-up, is this one. So where I talk about, so we could this so right, so we have these features. Basically, we can have blow up because of the amount of concrete categories, or so that happens if you have lots of inherent parameters that are big and they interact with each other. Or we can have blow up because maybe the inherent parameters are not that big, but so maybe there are not that many inherent parameters, but inflection tables are huge, and then you just have so many strings. Maybe we also sometimes this variance can really blow it up, which you can read that from the previous post. And then I talked a bit about how in Basque, I had the luxury of trying this kind of trade-off where first I had huge inflection tables, and then I replaced some of them with lots of parameters. Okay, this is just a pitch to go read my blog if you're interested in this. And then a concrete thing, which is very useful if you have a big grammar. So you can, if you want to test some slow grammar and only linearize, then you can open it in the GF shell using these two flags. So the retain flag is the one that, so retain keeps all the operas, and that's what allows you to use this command cc, compute concrete. And then no PMCFG is, as the name suggests, it doesn't compile it into this low-level format. So basically, this low-level format was introduced in GF to make parsing easier. So back in the days, there was a linearization only format, which meant that it was pretty feasible to actually linearize very complex grammars. And if you're interested in that, so you're very lucky, because at 4 p.m. today, we will have a talk about an attempt to recreate this linearization only PGF. Linearization only, so when I say PGF, I mean portable grammar format. So I know I'm kind of using the words PMCFG and PGF interchangeably where they are not related. Anyway, so the point is that you can open your grammar in this way, that if you only want to linearize, then you can do that. So if you need that info, you can also find that in that blog. I think that's probably good enough. We can stop here for any questions, comments. Anything? Oh. Yeah. Yeah, so today's talk was basically go read my blog. I'm not bothering to give a talk. Yeah. So let's just turn this off then. Right. So see you today at 4 p.m. Those who are interested, for talk about linearization on the PGF. Oh yeah, I can actually do all the housekeeping here now that there are some people around. So today 4 p.m. linearization on the PGF. 7 p.m. a talk about using GF in industry. 8 p.m. GF Dreams workshop. So that's all as it's in the schedule. But for tomorrow, so I have decided that we will do the virtual presentations at 8 p.m. Singapore time. So instead of having some random whole day allocated for that, we're just allocating 8 o'clock, so 8 p.m. Singapore, because that's a time where even the Americans have awakened. So we'll hopefully have the biggest audience.